In this part 2, we will see some of the example problems for uh, related to subnet masks. This is the problem. An ISP is granted the block 16.12.64.0/20. The ISP needs to allocate addresses for 8 organizations, each with 256 addresses. Find the number and ranges of addresses in the ISP block. ISP stands for Internet Service Provider. Find the range of addresses for each organization and the range of unallocated addresses. Show the outline of the address distribution and the forwarding table. This is the given question. So in this question, they are asking the students to calculate the number of addresses in the ISP block. So the given IP address is 16.12.64.0/20. So N, that is network prefix, small n is equal to 20, that is the mask. So a /20 network mask means 20 bits are used for the network address. So the formula for calculating the total number of address, capital N is equal to 2 power 32 minus small n. Small n is the prefix, network prefix. So 32 minus 20, you will get 12 bits. So 2 power 12, that is the total number of the host addresses. 2 power 12 is equivalent to 4096 addresses. So the range of the number of addresses in this ISP block is 2 power 12 is equal to 4096. This is the answer for the first questions. And the range of the addresses. So the range of the addresses in each and every block that starts from the given IP address 16.12.64.0 to 16.12.87.256. This is the range of addresses. So calculate the number of addresses needed for each organizations. So each organizations need 256 addresses. Since 256 is equal to 2 power 8, this requires /24 subnet mask. So you have to find the subnet mask. So how will you find the subnet mask means in a given IP address, the leftmost n bits you have to make it as 1 and the remaining 32 minus n, small n, that you have to make it as zeros. Then you can find its equivalent decimal notation, you will get the mask, subnet mask. So here 32 minus 24 bits, because you need 32 minus 8. Each and every block it requires 256 addresses. 256 is obtained with the help of 2 power 8. 2 power 8 is equal to 256. Totally 32 bits are there. So 32 minus 8, you will get 24. That is the subnet mask. So 32 minus 24 is equal to 8 bits per host. So determine the number of subnets needed. The ISP needs to allocate addresses for 8 organizations, each requiring a /24 subnet. Since we have 4096 addresses and each organization needs 250 addresses, we have enough addresses. So 4096 divided by 256 equal to 16 subnets are available, but we need only 8 subnets. As per this problem, we need only 8 subnets. So the subnets in the ISP block, we can allocate subnets from the /20 block. The first subnet will be you can calculate this from the given IP address 16.12.64.0/24, and the second 16.12.65.0/24, and the third will be 16.12.66.0/24, and so on. So each subnet will have 256 addresses. And determine the address range for each organization and the unallocated addresses. So we need 8 organizations. So the organization 1 requires the starting address 16.12.64.0 and the ending address is 256. The second organization again 16.12.65.0 and ending is 255. Third organization 16.12.66 and ending is 16.12.66.256, and so on. Up to 8 organizations we need it. So but available subnets are here 16. The remaining 8 subnets are unallocated address. So it starts from the IP address ranges from 16.12.72.0 to 16.12.87.250. These are the unallocated addresses. So this is the third question. Outline the address distribution and forwarding table. So this is the in this example we need only the 8 organizations. So the 8 network addresses are there, and starting and ending addresses of each and every network address. So the first one, it starts from 16.12.64.0/24. Ending address is 16.12.64.250. Similarly, for the second organization, it's network address 16.12.65.0/24 net ID, and the ranges of the address starts from 0 to 256. Like that, the last organization, that is 8th organization, is 16.12.71.0/24. This is the network address, and the range in this network starting address is 16.12.71.0 and ending address is 16.12.71.255. These are the 8 organizations available addresses. And in the second example, an ISP is granted the block 80.70.56.0/21. The ISP needs to allocate addresses for 2 organizations, each with 500 addresses, 2 organizations each with 250 addresses, and 3 organizations each with 50 addresses. So in this example, the given IP address is given, and the network prefix small n is also given, that is 21, and they need to allocate the addresses for 2 organizations each with 500 addresses, and 2 more organizations each with 250 addresses, and the third 3 more organizations each require 50 addresses. Find the number and ranges of addresses in this ISP block. Find the range of addresses for each organizations and the range of unallocated addresses. Show the outline of the address distribution and the forwarding table. Similarly, in this example, it is similar to the previous example. So in this case, the number of addresses, first you have to find the total number of addresses. Capital N is equal to 2 power 32 minus small n. Small n in this case is 21. So 2 power 32 minus 21. So you will get 2 power 11. This is the total number of addresses in this network, and the ranges of the addresses, it starts from 80.70.56.0/21 to 80.70.63.255/21. So first 512 addresses are there in this ranges, that is 80.70.56.0/23. This is the solution for the second question in this program. In this problem, 80.70.57.255/23. So first you have to find the subnet mask. How to find the subnet mask? So in this case, the small n is equal to 21. So you have to start from a left side. In the given IP addresses, you can convert it into a binary form. So from your left side, the first 21 bits are set to 1, and the remaining 32 minus 21 bits, that is the remaining 11 bits, are set to 0. Now you can find its equivalent decimal notation, that is your subnet mask. So first you need the 512 addresses that are in the ranges from 80.70.58.0/23 to 80.70.59.255/23. So 512 addresses are in this case. Again 256 addresses. Again the next address, you can start from 80.70.60.0/24 to 80.70.60.255/24. 256 addresses are there. Again to another 256 addresses, you have to make it from the next one. So 80.70.61.0.24 to 80.70.61.250/24. 256. These are the second group, and the third organization groups, you can have 80.70.62.0/26 to 80.70.62.63/26. 64 addresses. Similarly for the next 64 and another 64. These addresses are always assigned in the powers of 2. So these are the allocated addresses for the above required organizations, and the unallocated addresses 80.70.60.192 80.2/26 to 80.70.63.256/26. These are the unallocated addresses. So you can, this is the explanation of the above problem. So the number of addresses in the given ISP, that is capital N is equal to small to equal to 2 power 32 minus small n. Small n here, n is equal to 21. So 2 power 32 minus 21, you can have 2 power 11. So 2 power 11, that is 2048 addresses are presented in the given block. So the first address can be calculated by covering the given addresses into a binary format and performing the AND operation. This is the second method which I explained in the part 1 of this section. So performing the AND operations with the subnet mask. So how can you find the subnet mask? So for the given IP address, you have to convert it into its binary form. So take the left 21 bits, make it as all 1, and the remaining 32 minus 21, remaining rightmost 11 bits you have to make it as 0. Then find its equivalent decimal for address, that is your subnet mask. So in this case, the left side 21 bits are as per your IP addresses. You can make it, and the remaining 32 minus n, that is 11 bits, you can make it as 0, that is the given address. So then next you have to make it as a subnet mask. So given address, and you have to perform the AND operation, and the subnet mask is left 21 bits are 1 and the rightmost 11 bits are in zeros. This is your subnet mask. Now you have to perform the AND operation between the given address and the subnet mask. So you will get this is your first address. Therefore the first address in the decimal format is 80.70.56.0/21 by adding 2047, because the total number of the addresses is 0 to 2047. Actually 2048 addresses are there. It ranges from 0 to 2047 addresses. To the first address we can already got, that is 80.70.56.0/21, and the remaining addresses and the last addresses in this block is 80.70.63.255/21. So the range of the addresses 80.70.56.0/21 to 80.70.63.255/21. These are the explanation for the above problems, and this is the block allocations. So the first organization requires 2 blocks which are 512, and the second organization that requires 2 more blocks, 256, and the third organization that requires another 3 blocks that are in the ranges from 64. So these are the other things. So this is the alternate way. So the total 32 minus log 512 to the base 12, you will get 23. So like that you can do the calculations in another way. So this is the solution for this problem. So example 3, an organization is granted the block 130.56.0.0/16. The administrator wants to create 1024 subnets. Find the number of addresses in each subnet. Find the subnet prefix. Find the first and last address in the first subnet. Find the first and last address in the last subnet. So they need 1024 subnet. First you have to find the total number of addresses in this subnet and subnet prefix. For the first and the last subnet, you have to find its first and last address for the first subnet as well as last subnet. These are the questions. So the solution for this question is, so the small n is equal to, in this case, 10. So 2 power n, that is equal to 1024. Here 2 power 10 is equal to 1024, therefore n is equal to 10. The address given here is class B address, therefore the default mask is /16. This is the default mask. So the 10 bits are required for the subnets, and hence the required subnet mask is 16 plus 10, that is equal to 26. In dotted decimal format it shall be in 192. And therefore the subnet mask will be 255.255.255.192. This is the first answer for the first questions, and the remaining bits must be used for the address in each subnet, that is there will be 32 minus 26, that is equal to 6 bits available for the address component. Therefore, there will be a total of 2 power 6 is equal to 64 bits available. Also, 2 bits per subnet cannot be allocated, and hence each subnet mask will be able to maintain 62 valid addresses. The first address in subnet 1 is equal to 130.56.0.1, and the last subnet is and the last address in the first subnet is 130.56.0.62. The first address for the block can be calculated by ANDing the address 130.56.0.0 with the subnet mask, that is in this case /26. So you have to convert into its equivalent binary. So the given IP address, and this address cannot be allocated, so that we will consider the next address. Again it is 130.56.0.1. In the similar manner, the last address that can be allocated before the broadcast address will be 130.56.0.32, and the first address in the 1024 subnet is equal to 130.56.255.193, and the last address in the 1024, that is last subnet, is 130.56.255.254. So this is the solution for the above problem. Next one is FLSM, fixed length subnet mask. In FLSM, every subnet has the same number subnet mask, that is /n should be same for all subnets, and therefore the same number of addresses, even if some networks don't need that many. And the working of FLSM, first you have to start with the main network. For example, 192.168.0.0/24. Decide how many subnets you need. Apply a single subnet mask to the whole network so that each subnet has the same /n. Assign these equal size subnets to different parts of the network. So this is the example. In this example, the given IP address 192.168.1.0/24 and need 4 subnets. So the formula for the number of subnets is equal to 2 power n, where n is equal to number of borrowed bits. So it needs the 4 subnets. In this problem, it requires the 4 subnets. So n is equal to 2 bits. So the 2 bits are borrowed. New subnet mask is equal to /26. So 255.255.255.192. This is the new subnet mask. Each subnet is equal to 2 power 6, that is equal to 64 total addresses. So here the first, you have to leave the first and last address. So the usable addresses are the 62. So the 4 subnets that each and every subnet, out of 4 subnets, each and every subnet use 62 usable address. The first subnet 192.168.1.0/26, second 192.168.1.64/26, third one 192.168.1.128/126, fourth subnet 192.168.1.192/26. So in this case, all /n are similar, so same. So this is the fixed FLSM, fixed length subnet mask. VLSM, variable length subnet mask, a technique used in IP addressing that allows you to use subnet mask of different lengths within the same network. Instead of giving all subnets the same size, that is which is used in FLSM, VLSM lets you tailor subnet sizes to actual needs, avoiding wasted IP addresses. So VLSM is useful than FLSM. The reasons are, it is very efficiency, assigns fewer IPs to small subnets and more IPs to the large subnets. And the second advantage is flexibility. It can accommodate networks of different sizes in the same addressing plan. Scalability is the third advantage. It makes it easier to expand without numbering everything. This is the example for the VLSM. You have a IP address 192.168.1.0/24 network and need a subnet for 100 hosts and a subnet for 50 hosts and 2 subnets for 25 hosts. So first you have to sort by size. So the maximum number is 100, one subnet which consists the 100 hosts, and the second 50 subnet that consists the another subnet that needs 50 hosts, and another 2 more subnets, each requires 25 hosts. So the 100 hosts, it needs 126 usable IPs. So that is equal to /25, that is 128 addresses. So second subnet 64, but the in that available range is 64 addresses, so it is a /26. And the next one is 25 host requires, but it is the ranges is from 32 addresses, so /27 range. Next you have to assign the addresses. So the starting IP address 192.168.1.0/25. This is allocated for the 100 host network, and the next one is 192.168.1.128/26 for the 50 host network, and 225 host network we needed. So two networks are needed. For the first 25 host network, the IP address is 192.168.1.192/27, and the second IP address is 192.168.1.224/27. So in this example, we are using the VLSM, that is variable length subnet mask. For the 100 hosts, the mask subnet, the /n is 25. For the 50, it is 26. For the 25 two networks, it is 27. This is the example for VLSM. Next topic is block allocation. The ultimate responsibility of block allocation is given to a global authority called the Internet Corporation for Assigned Names and Numbers, ICANN. So the number of requested addresses n needs to be a power of 2. The reason is that n is equal to 2 power 32 minus small n, or n is equal to 32 minus log 2n, log n to the base 2. If n is not a power of 2, we cannot have an integer value. That is the reason n should be a power of 2. The requested block needs to be allocated where there is an adequate number of contiguous addresses available in the address space. However, there is a restriction on choosing the first address in the block. The first address needs to be divisible by the number of addresses in the block. The reason is that the first address needs to be prefix followed by 32 minus n number of zeros. The decimal value of the first address is then first address is equal to prefix in decimal into 2 to the power of 32 minus n. That is equivalent to prefix in decimal into capital N. This is the example. An organization is granted a block of addresses with the beginning address 14.24.74.0/24. The organization needs to have 3 sub-blocks of addresses to use in its 3 subnets, one sub-block of 10 addresses, one sub-block of 60 addresses, and the one sub-block of 120 addresses. Design the sub-blocks. This is the questions. So first you have to make the capital N, that is equal to 2 power 32 minus small n. In this case, small n is equal to 24. So 2 power 32 minus 24, that is equal to 2 power 8, 256 addresses in this block. So the first addresses, you can obtain the first address with the help of the given formula, that is the n number of leftmost n bits, you have to make it as 1, and the remaining rightmost 32 minus n bit, you have to make it as a 0, and convert this binary to a decimal, you will get a first address. Similarly, for the last address, the leftmost n bits, you have to make it as it is, and the remaining rightmost 32 minus n bits, you have to make it as 1. So you will get for the given IP address, you will get the last address. So the first address in this case 14.24.74.0 by 24. Last address in this network 14.24.74.255 by 24. To satisfy the third requirement, we assign addresses to subblocks starting with the largest and ending with the smallest one. So the starting highest is the 120 addresses, and it is not the power of 2, so we have to make it a power of 2, so 128 addresses. So the subnet mask for this subnet can be found at n1, that is equal to 32. You can use the log 128 to the base 2, that is equivalent to 25. So the first address in this block is 14.24.74.0/25, and the last address is 14.24.74.127/25. And the second subblock, it requires the 60 addresses. Even it is not a power of 2, we allocate 64 addresses. 64 addresses is the power of 2. So the subnet mask for this subnet can be found as N2, that is 32 log 64 to the base 2. You will get a 26. So the first address in this block is 14.24.74.128/26, and the last address in this network is 14.24.74.191/26. And the third smallest block that requires 10 addresses, it is also not a power of 2. So we have to allocate the next highest powers of 2, that is equivalent to 16. So the subnet mask in this subnet can be found. N3 is equal to 32 log 16 to the base 2, that is equal to 28. So the first address in this case 14.24.74.192/28, and the last address in this block is 14.24.74.207/28. Network address translation. This is the NAT. This is the technology that allows a site to use a set of private addresses for internal communications and a set of global internet addresses, at least one global internet addresses for communication with the rest of the world. The site must have only one connection to the global internet through a NAT capable router that runs the NAT software. So this figure shows the NAT addresses. The first addresses, the network address, is particularly important because it is used in routing a packet to its destination network. So it consists the number of networks, m number of networks, network 1, 2 and so on. All the networks are connected to a router, and the routing process, so it takes the destination addresses and from this one it finds the network addresses. So it uses the router uses the forwarding table. It consists the network address and the interfaces. From all those informations, it will find out the destination network address. Network address resolution, that the private network is invisible to the rest of the internet. The rest of the internet sees only the NAT router with the address, in this example 200.24.5.8. So site using the private addresses, so you can for private address, so many IP addresses are out there. Instead of using the private IP addresses, we can assign one private addresses, and this address we can use the NAT router to connect this private network to the rest of the world, that is internet. So in this NAT we can have a one private addresses and one global addresses. For the outside world, this one global address is visible to the internet. Address translation. All of the outgoing packets go through the NAT router, which replaces the source addresses in the packet with the global NAT addresses. All incoming packets also pass through the NAT router, which replaces the destination address in the packet with the appropriate private addresses. So this is the how the addresses, the private addresses can be replaced by a public address. Similarly, the public address will be replaced by a private addresses. This is the scenario it is given in this figure. Translation table. Using one IP addresses. A translation table has only two columns, the private addresses and the external addresses, that is the destination address of the packet. When the router translates the source address of the outgoing packet, it also makes note of the destination addresses where the packet is going. When the response comes back from the destination, the router uses the source address of the packet to find the private addresses of the packet. So the private network and also the translation table is there. It consists only the two addresses, private addresses and one of the universal addresses. And S stands for source address in this diagram, D for destination address. And first make the table entry, next change the source addresses and access the translation table and change the destination address. This is the process happening. using both IP addresses and port addresses. This is the 5-column translation table. It uses the private address, private port number, external addresses, external port number, and the protocol, transport protocol, which we are using for transmission.